Good afternoon, everyone. My name is Enrico, and today I'm going to present my paper with this title, You Can't Be Me, Enabling Trusted Paths and User Sub-Origins in Web Browsers. So this is a joint work with Yaoqi, Prateek, Saxena, and Zhenkai Liang from National University of Singapore, as well as Xinshu from ADSC Singapore. Okay, so the authority of the user in the present web is represented by the origin and also the session ID, and also the sensitive user own data that is loaded into the web browser is essentially tied to this origin and the session ID. However, an attacker can launch the so-called script injection attacks, wherein an attacker is able to inject arbitrary JavaScript payload into a user's web session. And once the malicious script gets injected, it has unfettered access to your sensitive user own data like your credit card numbers and so on, as well as your privilege requests tied to the user, such as setting someone as an admin or doing some banking transactions. And since this malicious script running inside the user session and can do some malicious activities on behalf of the user, these bad scripts can essentially become me. Okay, there have been many reports suggesting the prevalence of script injection attacks, as well as the damage that this kind of attacks cause. According to the Fair Reason research paper, roughly 9.6% of all Alexa's top 5,000 websites are vulnerable to the so-called DOM XSS, which is a subset of script injection attacks. In addition, roughly 1/4 of all web vulnerability that were reported are actually XSS. Okay, so to prevent these script injection attacks, the web has the following first-line defenses. First, it has SSL indicator, which can be used to indicate whether some contents are delivered to some untrusted channel or some trusted channels. Secondly, the web has same origin policy. Also, the web developer can do some sanitization at the application code. And there is this SSL auditor, which can be used to prevent script injection into a session. But we argue that this kind of defenses is not efficient in the presence of a malicious scripts already running into a user session. These first-line defenses aims at preventing the script injection attacks in the first place. And therefore, we have to resort to the second line of defense. And now, the web has content security policy as the second line of defenses. Also, we argue that content security policy is not enough because malicious script can easily inject some contents into the web application and then steal some users' own data. And really the question is, can we efficiently protect sensitive user own resources in the presence of malicious scripts already running in your session? So basically this attacker tries to take over your session. Okay, so the answer for this question is yes, we can. And turns out it has been challenging and it's very difficult to protect because there are many vulnerable channels on the web that an attacker can do to steal your data. Let me see one by one. First, the attacker can compromise your input channel and intercept any data that is entered by the user. Secondly, the attacker can tamper with the data that is displayed to the user. So in this example, you see that the attacker tries to change the content from 10,000 to 20,000, okay? And the third, there are many sensitive data in your web page, including your credit card information maybe, session ID and so on. And all this data are accessible by the attacker when it is running inside the user session. And lastly, an attacker is able to create network requests to the web server thanks to the browsers, to the API that is provided by the browsers, which is called as an XML HTTP request. And as part of our contribution, we propose to augment the web with the following notions. First, we introduce the notion of user authority, which complements the currently existing web origin by adding the notion of user principal. Okay, and secondly, we introduce a novel primitive which we call as a sub-origin, which essentially is a component that can isolate privileged data state and code within a web origin. And the third, we introduced the notion of trusted path, which is secure data channels between the real web users up to the trusted program at the web server. And as we will soon see in our evaluation, our approach is actually easy to adopt. It achieves high TCB reduction, and also it incurs only negligible performance overhead. And these are the scope of and assumptions on our paper. So what we consider is the following. First, we assume the standard web attacker, where an attacker is able to exploit some vulnerabilities in the web page, and also exploit some vulnerability in the malicious extensions, such that it will be able to do some script injection attacks. Secondly, we assume the uncompromised server, as this has been studied extensively. And the third, we assume the benign user, meaning that the user will not do any malicious activities inside his own user session. And the fourth, we consider only the JavaScript-based attacks. And our paper precludes the following. First, we assume the uncompromised web browser, and also any kind of script attacks such as Flash or Java-based are out of scope. And now, in the next couple of slides, let me show you in conceptual idea on how our design works, okay? And our design protects your sensitive user data since the very beginning you visit a website. So whenever first you visit a website, you will face this login page. And since this page is vulnerable to script injection attacks, the first problem that you will face is an attacker is able to compromise your input data. And the solution for this problem is we need a browser support such that the browser will be able to render some tamper-proof HTML element into the web page. And these tamper-proof HTML elements, you can easily input user data, and the data that you entered into this element will not be accessible by any malicious script. Okay, is that enough to protect sensitive user own data? Yeah, I think it's not, okay? And so there are some other problems that we try to tackle. The secondly is the attacker can also spoof or create some fake HTML elements and try to trap the user into entering his credential information. So for example, the attacker can create some fake HTML elements and ask the user to enter his credit card information, for example. And to tackle this problem, similarly to the input elements, we also need a browser support to be able to render spatial display elements, and this element will get rendered with a color background, so that the user can easily verify some authentic elements simply by checking the color that is rendered with the color indicator which is shown in the Chromium, in the URL bar of the browser. Okay, so this looks good. Then after you have this two input and display and input channel, now data that you entered will be remain in the browser memory. It won't be accessible to the malicious script. And the problem next is, why can't the attacker do the same thing? So why can't the attacker also include the same application code and do some phishing attacks and try to trap the user into also inputting the username and password? So this is the typical authentication mechanism in the web. So you will enter your username and password, and then this credential information will be sent over the network. And in the case of phishing attacks, this credential information now will be accessible to the attacker's web server. Okay, so the key idea here, we don't want this credential information to be leaked outside this browser memory. And how do we authenticate ourselves to the web server but without revealing our credential information? So the idea here, we will modify the web, the authentication method in the web by adding the way which is called the PEG protocol, which is a protocol that can mutually authenticate browser and the web server without actually revealing credential information over the network. So I won't go into the detail of this fake protocol, but this protocol, in order to be successful, it requires both the web browsers and also the web server to be having the credential information. And if both parties have the credential information, the protocol will be successful and some secret session key KS will be derived. And this will be stored securely on the web browser. Okay, once the user successfully authenticates himself to the web server, now the web server needs to send application code in order to be run in the web browser. And a typical web, what the web server does is it will send this HTML and JS code, it will get rendered and processed in the web browser. And as I've mentioned earlier, since this is run in the origin, so malicious script can also have access to this sensitive user own data. So the sensitive user own data here is the account number, this one. Okay, in order to tackle this problem, the key idea here, we would like to privilege separate some sensitive data and some trusted code from the rest of the application code. So we have the untrusted application code, which is this HTML and JS file, and also we have this sensitive data and trusted code, which needs to be checked on its integrity and authenticity before it gets run in the web browser. And also, we need some component in the web browser to be able to run and execute this data and code, right? So the idea is we'll have this component in the we need some component in the web browser, and this component will execute this data and code. And only code running inside this component will have access to sensitive user own data. So in this case, only code running inside this box will have access to the account number. And since only trusted code running inside this black box, this box, malicious script running outside this component only have the origin authority and also will not have privilege to access the sensitive user own resources. Okay, at this stage, I hope I can convince you that we can protect your sensitive user own resources at the client side. But the attacker can do one more attack. So this is the example. Since the attacker has access to the XML HTTP request, it can also create some arbitrary request to the web server, right? Okay, and the idea to solve this problem is we need to introduce some kind of authorized HTTP request which can only be created by some trusted components. And these components will create this HTTP request, and the web server needs to know whether some HTTP requests are authentic or not. And the way the web server distinguishes the authentic HTTP request is by following. So first, since we have KS as the root of authority on the web, we will derive some secret token T, and this token will be attached to any HTTP request which is originated by some trusted components. And this HTTP request with this secret token will be sent to the web server, and the web server can easily validate whether this HTTP request is authentic or not. And since the malicious script doesn't have access to this secret token T, then his request will be dropped by the web server. Okay, that's a conceptual idea on how our design works. Now let's get into the real implementation and how do we implement this in a real browser. So I've mentioned earlier that we already have these tamper-proof HTML elements, and also we are able to render this secure display content to the web, and therefore we establish the notion of secure display channel and secure input channel on the web. And secondly, I keep telling you about this component, but I haven't really told you what the name is, right? So yeah, we have the name for this component. This is called as a U-frame, which is a component with higher privilege than on origin and has access to the sensitive user own resources. And also, this UFrame has an API, which is a privileged API that enables this code to create some secure input and display element. So yeah, in this case, since only this component has access to sensitive user own data, we built the secure session data channel and also the secure input display channel on the web. And if you see on this UFrame has the notion of user authority because it has access to the user data. And also, since any object or data inside this component is isolated from the rest of it, the rest of the application code, it also has the notion of sub-origin. And lastly, since any authorized HTTP request will be attached by a token, this can be easily checked by the web server, and therefore we also built the notion of secure request channel on the web. And let's see how it works. So the user will enter some data. This will remain in the browser memory in this example. And some trusted code inside this UFrame may get access to this data. And it will do some processing on it. And once it needs to create a request, it will call some privileged API, which eventually creates some HTTP requests along with the token to the web server. So now the web server can easily check this authentic HTTP request. And yeah, already told you about these four channels, namely the secure input channel, secure display channel, secure session data channel, and the secure request channel. And these 4 channels on the web, we built this successfully on the web, and these 4 channels constitute the notion of trusted path on the web. And since we also have the component which we name it as the UFrame, this has the authority of the user, and also this has the notion of sub-origin. Combining these two with the trusted path on the web, we have the system or a design that we name it as a UserPath. And this is how we implement UserPath. We patch Chromium version 12 by adding less than 500 of C++ code. So what we do is we also add client-side page plugin on the web browser, as well as the server-side page module. And in addition, we also modify the PHP application, which I will show you later. And we go to the last section, so I will show you how we evaluate our system. So yeah, in terms of the evaluation, these are 3 questions that we try to answer. First, how many lines of codes that we need to add to the web applications in order to adopt UserPath? And secondly, how big is the TCB reduction after we adopt UserPath? So TCB is the component in the application code that needs to be trusted. And the third is, how big is the performance overhead after you adopt UserPath in the web applications? And here is our evaluation setup. We evaluate our system on 20 open source PHP applications. And this covers a wide variety of PHP functionalities, such as e-commerce, social network apps, and so on. And these are some examples of sensitive user-owned data that we want to protect for this particular application. So yeah, just for your information, ELK is an open source social network apps. And we also try to look into each applications and find out how many vulnerabilities are there in these applications. So we only focus on the XSS and CSR vulnerabilities, and we found 325 XSS and CSR vulnerabilities which can potentially be used to steal sensitive user-owned data. Okay, let's answer the first question. In terms of the adoption effort, we successfully retrofitted 20 PHP applications. So what we do is we modify web page that contains sensitive user-owned resources, and we measure the LLC number that we need to add to the PHP code. And for these 8 typical functionalities, we got on average only 149 lines of code needs to be added to PHP applications. And in terms of TCB reduction, what we do is we try to compare the initial TCB which is the size of the web page of the application. Why do we need to measure the size of all the web page? Because in terms of the script injection attacks, we need to protect. Basically, we need to trust all part of the web page in order to protect the sensitive user-owned resources. And as for the final TCB, we measure the size of the UFrame code because it's the only component that we need to trust on the application code. And this is how we got the reduction. So we just divide the initial TCB with the final TCB. And yeah, these are the reduction for all 8 typical functionalities for these applications. And our system achieves a high TCB reduction ranging from 8 times to 264 times. So yeah, this essentially means that only small part in the application code, very small part in the application code that we need to trust. And lastly, in terms of the performance, we evaluate the performance on our Chromium version 12, the modified one. And then what we do is we measure the time taken within the first time you log into the web application and then successfully log in. And then after all the resources are loaded into your web browser. And we argue that this already covers all the important functionalities that we propose in our idea, such as the secure login and also the secure authority delegation. And we measure this in seconds. So yeah, the result is our system incurs only negligible performance overhead. So the performance overhead is only 2.3%, which is relatively small in the large-scale deployment. So yeah, let me conclude this talk by the following. First, we augment the web with the 3 missing notions on the web. First, the notion of user authority. The second one is the notion of sub-origins and the trusted path. And our solution is a complete second line of defense to protect sensitive user-owned resources in the presence of malicious script running inside your session. And our system has practical applications. We evaluate our system on 20 open source PHP apps. It's very easy to adopt. It achieves high TCB reduction. And also, it incurs only negligible performance overhead. And lastly, yeah, the source code is available. You can access it anytime. Yeah, thank you very much, and I'm happy to take questions.
I may have missed something, but you mentioned in the beginning that content security policy is not sufficient enough.
Yes.
So let's say we have a website with a very restrictive content security policy. Let's say we only allow scripts from that same domain and we don't allow inline scripts.
Okay.
How would the attacker inject his malicious code to begin with?
Okay, what these malicious extensions can do is they can just remove the CSP header from the request when it comes into the web browser. So we are talking about malicious extensions, and these malicious extensions can do everything.
Oh, all right. So you're saying if the user or if the attacker has control of what is sent to the user.
Yeah.
All right.
So we are talking about malicious extensions. Also.
Ah.
It has ability to inject some script into a session also.
All right.
Okay. So just to be sure, there is no legacy support at all, right? You need a special browser with a special server, and there is nothing that you can give to pages that are already there.
Yeah, we need to modify browser, correct, and also we need to modify the server-side code a bit. But we argue that the modification that we need to add to the existing platform is relatively small.
Yeah, over here. Yeah, but like referring to the first question,
Yes.
Aren't you lost anyway if the browser or an extension of it is kind of compromised and it accesses any information on the page?
Yes, and our design can prevent access from the malicious extension to the sensitive user-owned resources.
Wouldn't it be then just like, well, more general to kind of like change the extension APIs and so like, yeah, I don't know.
It's not that easy, right? Because if you are talking about sensitive user-owned data, it can be in any ways. You can just maybe create some fake login button and then ask the user to input some username and password. So it's not only some data resides in your web browser, it can be from anything else. And also the malicious extension can also create some requests to the web server. So I argue that we cannot just modify the API in the extensions to protect sensitive user own data.
So from a practical point of view, if until the point where all the browsers are modified to deal with this system, if you have a web server that want to use this functionality, you will, before serving the page, you will have to kind of figure out if the browser has or not the capability to handle what you offer, right? So what's the risk that at that time, the malicious extension or anything else, or a script that was there before, tells your browser, no, I don't support, and from there on, presents to the user what he expects, which is a nice coloring and so on, and basically, how can I know if the good browser I have and everything I have done actually is really working for me, or if it has been prevented from the very beginning before talking to the server?
Okay, so I show you this color indicator on the web browser, and this can't be controlled by the malicious script.
Sure, but my point is, you agree that at some point the server needs to figure out if the browser is capable of supporting those features, right? And if not, he will just serve a normal page, right?
Yes.
So what if my browser at that time, because it has already a malicious script in it, then says, in this negotiation phase, says to the server, no, I'm not supporting you. Even though it should, but it says, I don't. And from there on, this malicious script presents to me exactly that, this coloring that I'm expecting to see, but I don't know that actually this is made up by the malicious script as opposed to the right protocol that you have defined. You see my point?
So you're saying the server hasn't implemented the PIC, or?
No, I'm saying that not all browsers will support your protocol, right? So until they all have it,
Okay.
your server must be able to cope with these non-compliant. So what if the malicious script says, I'm not compliant, even though it is, but because the client, the user had done everything he thought was right, he had the right version and everything.
So in order for the protection to work, we need the browser and the web server to be equipped with this idea. So if the browser doesn't support UserPath, we can't protect your sensitive user own data.
Yes, but what I mean is before doing the UserPath, what if the first time the browser contacts the server, right? At some point you will need a negotiation phase, so to speak, or you need to announce if yes or not you have the capability to support. What if the malicious script at that stage says to the server, you know, I'm coming from a browser that does not support your UserPath thing. So don't even try to serve me that page, and shut you down even before starting.
Okay, I think that will not work, in our case, because that kind of attacks will happen.
Okay, sounds like something to discuss on the tram.
Yeah, maybe we can take this.
when we go to the restaurant. Excellent. Okay, thank you very much. Great talk.